Okay, good afternoon, everyone. Welcome to this seminar we are organizing under the Geophysical Flows Lab Research Initiative. We have with us Professor Philippe Odier from the Physics Department at ENS Lyon in France. He's already visited us last year for a month. He's again with us for a few weeks this time under a Spark project on resonant trade interactions and stratified shear flows. This project is a collaboration between Philippe, myself, and Professor Anubhav Roy in applied mechanics. His expertise is on experimental modeling of rotating and stratified flows. He's going to tell us today about some of his work on internal gravity waves.
Hi everyone. Sorry I have things in my ears. It's not that I'm listening to music while talking to you, but that's for the people who are online, who can so that they can actually listen to what I'm saying. So yes, I'm going to present you kind of an overview of what we did in the lab, centered around mixing and transport in the ocean, and of course using internal waves. So the people involved in this work are displayed here. So as you can see, it's a work that has extended over a little more than 10 years, starting with the PhD of Philippe Odier starting in 2011. Then there was a postdoc, Ivan Dossman, for a year, and a second PhD student, Paco. They followed Baptiste, and last PhD student Samuel, who followed Paco. And the work was supervised jointly by a team of three, who you can see here. You may have met, especially Thierry Dauxois, who is actually here, I think, in a little more than a week. He is now a big shot at the CNRS in France. He's visiting with this responsibility, but he's a researcher in the same field, and Sylvain Joubeau here. So to start with, I'm going to present the main motivations of our work. I'm just going to raise down the volume because each time I press here, I hear a beep in my. Let's see. Yeah, that's better. So here is a picture of the ocean. It's a picture everyone knows about the ocean circulation, also called the meridional overturning circulation, MOC, here in around the oceans of the globe. And the idea, or the concepts behind the circulation is, on one side, you have regions where you produce denser water. Usually, of course, there are regions at higher latitudes where the water is colder and saltier, when it turns into, it freezes, most of the salt stays in the liquid phase, so it becomes also denser for this reason. And these denser waters here, they tend to go to slow down the gravity towards the center or the more meridional regions, where usually the ocean is deeper, so you actually have people call a gravity current here. But of course, if you would have only that, after some time, then you would have all the water, all the heavy water down at the bottom of the most bottom part of the ocean, and the light water at the top, which is not the case. We know that there is a circulation, so somehow it has to come back. Once it's gone down, it has to come back up. And there is a hypothesis based on, made by Munk and Wunsch already in '66, so that was even before I was born. The idea is that it comes back up everywhere via turbulent diffusion. So there is some mechanism that actually converts kinetic energy into potential energy or mechanical energy from some agitation there is in the ocean into potential energy, because when you mix water, it means you take the heavy water, you bring it up, or the light water, you bring it down. This corresponds to a conversion of mechanical energy into potential energy. And the hypothesis was that this was done via turbulent diffusion. So the diffusion, not the molecular diffusion, but the diffusion enhanced by the turbulence everywhere in the ocean. And so, yes, that's just what I said here about conversion of energy. So if you try to write a few equations about that, so here is the equation for the evolution of density here. And there's, of course, this term that involves a correlation between density fluctuation, the prime means fluctuation, density fluctuation, and velocity fluctuation. So the definitions are here. Your overall density is separated into a mean component and a fluctuating component, same for velocity. And so if you extract from this equation the main terms in the vertical, you get what's called an advection diffusion balance, where the advection is here. There is a certain velocity of transporting the density. And it's balanced by the diffusion, but the diffusion due to these interactions between velocity and density fluctuations. And so the usual, most classical hypothesis is that you will parameterize this term, because one cannot compute it directly. So one parameterizes this term, saying that it's proportional to the overall density gradient. And because this relation here, this is a flux and this is a gradient, so there's this usual relation between fluxes and gradients, like Fourier law or Fick's law for particle diffusion. So the idea is the same. There is some diffusivity here, except that it's a diffusivity associated with turbulence and not with molecular agitation like the usual diffusivity. So it's called kappa T, and that's an assumption, of course. So you can re-inject this into this equation. You get this here, or you can rewrite in this way. So kappa T here is W times the ratio of the first to second derivative or vertical derivative of density. And so now you can try to compute some values for that in the ocean. So W can be estimated either by radiocarbon data, local estimates, or by global estimates using the balance of bottom water formation. Are you seeing? Because I'm trying to, otherwise I don't see the screen myself, which is and so these are just derivatives, I mean, of the density first and second. So from a density profile, we can get these values. And in general, the order of magnitude gives a centimeter per day for W, and this ratio is just the length, and so it will be 1,300 meters on average, and that gives you a diffusivity, a turbulent diffusivity of a centimeter square per second, which is many times larger than, of course, than the molecular diffusivity, which is of the order of 10 to the minus 5 centimeters square per second for salt, at least. Temperature is a little higher, but still it's much lower than that. So now the question is, there is this everywhere in my sentence here, which was the hypothesis initially of Monk and Bunch, but is it really everywhere? And there is this very famous plot that was that was computed from measurements in the Brazil basin by Poulsen in 1997, showing, so he actually measured in the ocean this KT parameter. So that's centimeter square per second. So the value of 1 centimeter square per second is green, corresponds to green, yellow actually. So you see that there are regions in the Brazil basin here on the left that have a much lower, like one order of magnitude lower than the expected value here. And there are some regions close to this place where you have a very rough topography that have values all the way up to 20 times the expected value. So it's actually doesn't seem to be everywhere. It seems to be in some places, some localized places, there is a lot of turbulent mixing, and in other places there's not. And so what are the local mechanisms that actually create this turbulent mixing? Well, internal waves is a good candidate. So I will come back in a second to exactly what's an internal wave, although maybe most of you know, but I will just quickly go through that. Internal waves, they are likely to be generated near rough topography because the presence of the topography and the tide going back and forth around the topography, that's one way of creating these waves. So here you have lots of little mountains, sea mountains, where you can actually generate these waves. And they can be unstable, and that's one of the main themes that we studied in our last 10 years. They can be as unstable, leading to small-scale secondary waves that are more prone to induce irreversible mixing. Because, of course, when you say mixing, you stir the things, but to actually have mixing in a way that you actually create some potential energy or increase the potential energy, you actually need to have the irreversibility of phenomenon to take place. So, and that takes place at smaller scale. So you actually need, once you do this mixing, you actually need the phenomenon to take place at small enough scale that actually the actual molecular diffusivity plays a role, or diffusion plays a role to actually induce irreversible mixing. So in a way, these waves, they are good candidates for these two reasons. They can also travel, that has been of course observed, measured in the ocean. They can travel long distances, so they can travel long distances and then suddenly for some reason, because they get amplified or something, they start to overturn and to create mixing. So it's a really nice candidate for this, to understand this mixing. So
that measurement in the field of KT, is that from the expression that you had in the previous slide, like local measurements of vertical velocities and density?
Yes, actually, it's what people measure is epsilon. So it's the turbulent the epsilon term, which is velocities radians. So they use probes that actually measure very precisely, but very short, with very accurate resolution. They measure the velocity in different directions, and so that you can have access to the velocity gradients, which gives you the epsilon, which is the turbulent. I forgot the term.
Dissipation.
Turbulent, the dissipation, and there is a relation that's of course based on some assumptions, but there is a relation between KT and epsilon. And so once you measure epsilon, you can actually get that's how they do it in the ocean. Yes. So what is an internal wave? So internal waves are ubiquitous in the ocean and in the atmosphere as well. Here is a picture of internal waves. So internal waves, as their names say, they are internal, so you don't actually see them from above, except that they create some, they actually create at the surface some changes in the sun glint, in the reflection of sun, simply because they create regions where they actually come up, and there are regions where the fluid, where there is a jet going up, and other where it's actually going down. And so this changes actually the roughness of the surface of the water. And so when the sun reflects on this surface, well, if it's rough, it gives you a certain impression. If it's not rough, it gives you a different impression. And it reflects better if it's not rough, and if it's rough, it diffuses everywhere, so that if you're at a given point, you see less light reflected from the sun. So you actually get a manifestation at the surface of the presence of internal waves in the ocean. But so that's a way to identify them. But of course, they can also be measured by measurements inside the ocean, but it's more complicated, of course. And so it's a gravity wave in a continuously stratified fluid. So that's the case of the ocean and the atmosphere. Again, it's a continuously stratified fluid. Stratified meaning the density depends on depth, on height. So if you take a fluid particle, this region is less dense, this region is more dense, you bring this particle up, and then you let it live its life. It will come down because it's heavier here than its environment, and it will come down further than it was before just by inertia. And this will create an oscillation, and this oscillation can propagate, and that's a wave. The propagation of an oscillation, that's the definition of a wave. So in a way, it's exactly the same mechanism as a wave at the surface of the ocean, except it's a bit different because it's in a continuously stratified fluid. So there's an important parameter for internal waves. It's the Brunt-Weisel pulsation or frequency, which is defined using based on the gradient of density, d rho dz, and then of course g, the acceleration of gravity plays a role, and that's the mean density here. And so for these waves, the dispersion relation is quite peculiar because usually dispersion relation relates frequency and wave vector. Here it relates frequency to a certain combination of the different components of the wave vectors that actually happen to be simply the sign of the angle of the wave vector with the vertical, with the direction of gravity, which is vertical. But that's important, of course, is that it's the direction of gravity. So in a way, your dispersion relation does not involve the actual wavelength as usual dispersion relation. It involves just the direction. So you choose your frequency, you choose the direction in which the wave will propagate, which is kind of interesting. And that's actually, sorry, go through that again. That's one of the reasons that made us physicists, because Mani said I'm a physicist, I'm not an oceanographer, I do experiments in physics, but physicists got interested in these waves because they have these peculiar features that made them interesting just as objects of study for physicists. And there's another interesting feature which you will see later, that the phase velocity is perpendicular to the group velocity, which is also kind of interesting. So you fill a tank with a stratified fluid. So there's a method called two-bucket method. So you have one bucket with salt water, one bucket with fresh water, and these two, they communicate here. And here you have a mixer on here, so that when you start pumping water from here into here, it's actually, as the water is pumped, so it fills here, but as the water is pumped, you have salt water that comes in here and get mixed, so that versus time, the concentration of salt increases linearly here in this, so that keeps filling at the same, below the previous levels. So at the end, you get a nice and linear, so that's actually the measurement, so it's a nice and linear profile of density, which allows you to compute the n, and n is a constant, so the Brunt-Weisel frequency, if this gradient here is constant. So that's how you create the stratified fluid. So this is a picture, this is a little movie that was actually not made by myself, but by my host some time ago, Mature, with Mathieu Mercier, Thierry d'Auxois, who I presented, and Thomas Picker from MIT, presenting actually how you generate the waves, because it was actually invented the first time by Louis Gostiaux, who was a PhD student of Thierry d'Auxois. And so the wave generator the idea of the wave generator is the following. So you will have, it's coming, so you have disks with off-centered holes, and so that when you rotate the disk, it pushes the plate back and forth. So here is an example. The disk is on a shaft, and because the hole is off-centered, it actually moves the plate back and forth like that. And so you can put the disks on the shaft with an angle at each disk has a different angle. And so you stack the plates, and then you fill with a linear stratification, so that at the end you get a profile. Well, you can't get a profile like that. You can't get any kind of profiles actually. So here, for example, that's a view from the side again. So here is a few plates that have this nice sinusoidal shape here. So that when you rotate the shaft here, you get this moving boundary with the desired shape that will force the wave in the desired time. So that's the whole idea of of these wave generators that we have been using for some time now. So now to observe internal waves, we use a method called synthetic Schlieren, which is related to the old method called shadowgraphy. You have a tank, you look at and behind the tank you have a grid, illuminated grid with lots of randomly placed dots. And you look at that with a camera through the tank. And because when you have a change of density, it implies that you also have a change in refraction index. It means that the way you will see the points will depend on the density, because it depends on the refraction index, where if the refraction index is constant, you see the point through a straight line, but if it's not constant, then the light will be bent, and you will see an apparent displacement of the points. So here is an example. I hope you can see it from a distance. So that's just a raw image of what the camera sees. So the generator is up there, and you can see that you have points here that move back and forth, well, apparently move back and forth. And so the idea is that then you can use the same tools you use for PIV. You may have heard more of PIV. PIV is just you identify particles. You put particles in the fluid, and you follow particles, and you see the motion directly. You measure the velocity through the motion of the particles. So here you actually see an apparent motion of these dots, and you can relate that to the index refraction gradient, and this is all directly related to the density gradient. So yeah, that's what I just said. So you look at the maximum correlation between two images, or between an image with waves and an image without wave. And this gives you the apparent displacement of the dots, which is due to the presence of the wave. So that's what we saw here. So yes, you get the gradient field of refraction index, you have a density gradient field, and so that's an image of the waves, the image once it's processed. So you get the same thing as before, except of course you see it better because you have colors and so on. And you were able to see that energy starts here because that's where the generator is, and it goes in this direction because initially all the energy was here and goes there. So the group velocity drawn here is in this direction, and the phase you were able to see. Maybe I should go back because that's nice. See again, you can see the phase. This is a line of phase, and it actually goes in, the phase goes in this direction. So the phase velocity here is perpendicular to the group velocity. So it's very obvious in this. Now, the interesting thing about these waves, and that's what I mentioned earlier, and why we got interested in studying them for mixing, is that they get unstable. So if you keep going, if you keep playing, here I'll stop the movie, but if you keep playing the movie for a while, and so that was the core of the study of the PhD of Baptiste Bourget here. So if you keep playing the movie, you see that after a while there is a disturbance that appears here and more starts to spread through the whole wave field here. It's not these nice red and blue lines as you had before, but you have something more complicated appearing. So that's an instability. And that creates smaller scales than what you had before. So that's interesting again for mixing. And so what is this instability? It's called a triadic resonant instability. Triadic resonant instability, which other people call it PSI, which is a parametric subharmonic instability. We'll just give a few explanations about these terms here. But I think this one does say more clearly what it is. It's an instability that implies three waves. That's why it's triadic. And that's resonant. I will show in a second what I mean by resonant. So if you look at the time evolution of the frequency spectrum, so you make a Fourier transform of the time signal at a given point, you get the frequency. So you see that's the frequency, the initial frequency, or the frequency of the primary wave. It was written in the previous slide, 0.74. That was the ratio omega over n. By the way, omega has to be always smaller than n because the ratio of these two is sine of theta, of course, larger than 1. So here, omega over n is for the 0.74, and after a few seconds, not that many, you see like 20, 30 seconds, no, even less, 10, 20 seconds, you see the appearance of secondary waves here. And if you make a cut at this level here, for instance, at this time here, you get these three peaks. And if you look at the frequencies precisely, so you have the 0.74 I was mentioning before, this one is at 0.5, this one is at 0.24, and interestingly, the sum of these two is equal to this one. So, and this is what we call the temporal resonance condition. Temporal because it's frequency, it's time frequency. And so you got omega naught here equal to omega 1 plus omega 2. Now, it's resonant in a second meaning because, sorry, there's this little discussion here. In the ocean, the viscous effects are negligible in the sense, well, it's the same viscosity, the sizes are bigger, so the viscous effects can be neglected. And in this case, usually you have omega 1 equals omega 2, and of course equals omega naught over 2, because this sum is still valid. And this is usually called parametric subharmonic instability, and the reason it's parametric is because when you do a parametric instability of an oscillator, you actually get frequencies that get half the frequencies and this kind of thing. So that's why it was called like that. So usually this one, people, especially in the ocean, they refer to an instability where you actually produce two waves at half the frequency. In the lab, you have strong viscous effects. So the two frequencies are different. You see 0.5, 0.24. So for this reason, we decided to actually change the name because people used to call all these instability PSI. But now I prefer to call it triadic resonant instability. So you can also play with the images a little more and try to do what's called or use the mathematical transform called Hilbert transform to actually extract from a series of images what belongs to a given frequency. So if you extract from a series of images what belongs to the primary frequency, you recover your initial wave, the one you had before the instability started, with a wave number that you can easily compute. Of course, here you cannot compute wave numbers, but here it's easy to compute the wave number because you have these lines and you can just measure the wavelength and so on. You do the same for omega 1, you get this. Do the same for omega 2. As noticed, you have a smaller scale here that you have here. Again, this idea that small scale is creating waves at smaller scales is interesting for mixing. And these three wave vectors, they actually sum up 0. So that's the second condition. You have a spatial resonance condition, K naught equals K1 plus K2 here. And so that's why it's called resonant triadic instability. So one thing all this study, these first results were the ones we got with the thesis of Baptiste. It had never been studied, so it's so much detail in literature before. We also measured or realized that there is a finite width effect in the sense that if you take this wave, after a while it becomes unstable and you get this. So these are the images I was showing you. And you take another wave, same wave number, same amplitude, so psi 0 is the amplitude here, same frequency, except instead of having 3 wavelengths, you have only 2. And in this case, interestingly, it remains stable. You never see the instability. So there seems to be an effect of the width of the beam here. So we call that finite width effect. And we actually we managed to model that effect by that's in addition to these quantities, the beam width seems to matter, and it seems to add a threshold on the instability because here it's unstable, here it's not. And so the idea, I won't go into details, but is that if you get a narrow beam, it means you have a narrow region where the 3 waves can interact, because of course, if the width is finite and the secondary waves have a different wave vector than the other one, they actually propagate outside the region of the primary wave, so that if the primary wave is narrow, there's less possibility of interaction, and so this reduces the growth rate. So And it can go all the way to actually canceling possibility of instability. So we, in a collaboration with Michael Lebars, who ran numerical simulations, because in the lab it's very difficult to do more than 3 or 4 wavelengths, but with simulation he was able to do 20 wavelengths, so go towards actually close to large, what you could call wide wave beams. And so we showed that there is actually a threshold due to the Now, what if you add rotation? Because of course these waves in the ocean, they are in the ocean, which is on the Earth, and the Earth rotates. So there is a component related to the rotation of the Earth in the waves that you see in the ocean. So what we did, and that was the work of Paco Morer in his PhD, we took our tank with a stratified fluid and we put it on the turntable. So that's the movie here. That's a tank with a laser illuminating it to measure what we wanted to measure, and we put that on a nice large turntable that we built in 2012 in our lab. And so when you do that, well, we did a lot of different studies. I'm not going to show everything, but this study is a bit complicated, but I'll try to explain it. So this is frequency, and this is rotation or Coriolis parameter, which is twice the rotation rate of the table. And so at no rotation, we were here, and this is the threshold because all the circles, the orange circles, they mean there is an instability, and all the blue crosses means there's no instability. So clearly there's the experiments where you see instability are at high enough frequency, and at lower frequency you have a threshold so that you actually don't get the instability. And now how does this threshold change with rotation? That's one of the results we showed. Well, it turns out that at some rotation of the order of 20% compared to the Brent-Weisela frequency here, you find cases where you do have instability, all these circles here, where at the same frequency, at the same wave frequency, but at no rotation, you would not have. So there seems to be an enhancement of the instability at certain F. And so that, of course, we try to relate with an observation that was done by Jennifer McKinnon in the ocean, that there is a critical latitude, because, of course, the Coriolis on the Earth, it's not the case for us, but for the Earth, the Coriolis parameter changes with latitude, so that they have so critical latitude at which at more of these instabilities that they observe in the ocean. And so we show that there is actually a critical frequency Coriolis parameter at which you have more instability. Then it goes up. The reason it goes up is that this region here is forbidden for the instability, and the reason is, of course, I haven't mentioned that before. I always said that omega needs to be smaller than n, but it also needs, when you have rotation, to be larger than the Coriolis parameter. That's if you write the dispersion relation, including rotation, you actually don't only you get a different dispersion relation than just omega over n equals sine theta. It's a little more complicated, and it implies that omega has to be within the range between f and n. And because of that, when you have an instability, your secondary waves that have a lower frequency, well, they cannot have a frequency that's lower than f, otherwise they won't exist. So because of that, this region here, there's a line that's forbidden, well, beyond this line for lower frequency, higher Coriolis parameters than this line, you cannot have instability. So obviously the threshold needs to go back up, and as we can see, there are no instabilities here in this region. Another thing we saw was these are the series of frequency diagrams, just the one I showed you before, but it was reversed, where we had the three frequencies, 0.5, 0.75, 0.5, 0.25, 0.24. Here you can see the three peaks. That's at zero frequency, and then we just shifted them in the same plot by a certain amount, just so that they're not on top of each other, for different rotation rates. So going from no rotation to large rotation, 0.45 f over n. And so you see that actually it seems that the peaks seem to get closer to one another, so that you get actually closer to the situation called PSI, meaning that the two waves are almost at half the frequency of the primary wave when you have rotation. So that's another observation we made. Now, one subject we tried to focus on, especially in the collaboration I had with Thomas Peacock at MIT, was studying internal waves in the Arctic. So why in the Arctic? Well, the Arctic Ocean is less and less covered with ice because of global warming. That's the sea ice extent as a function of time. So it started reducing after year, I can't read the years, but it's 2000, so before the end of the last century. And it reduced quite a lot. So that's in some multiple of square kilometers here. And so, of course, I told you before that the waves could be generated in the ocean by the tide going back and forth around the mountain. Another way to create a wave is if you create some motion at the surface, and then a storm, for instance, creating lots of motion at the surface would send some waves that would propagate towards the bottom of the ocean. But of course, if you have ice, you can have a storm, nothing will happen below the ice. So in a way, the fact that the Arctic Ocean is less and less covered with ice means that it's more subject to storms that will generate internal waves. So that, in a way, and that means that, of course, the dynamics of the Arctic Ocean will be changed with time by the fact that you reduce the ice cover. And that will in turn influence the dynamics in general of the ocean. So that's why it's an interesting subject, and lots of oceanographers make cruises in the Arctic to actually try to measure a certain number of things. And so we try to mimic, in a way, an Arctic storm internal wave generation. So an interesting thing in the Arctic is that you have a layer called a thermocline that's clearly marked, where you have a change of slope of the density versus depth. So in a way, a change of the value of n at some depth here. And so you have winds that blows at the surface. It will create some waves. And because there's a change here, the waves can either propagate through, or they can reflect on this interface and go back. And so we tried to, in a way, measure the internal wave energy transmission through a change of stratification. But when all the experiments we had done before, where you've seen our tanks, you generate the waves, and you have these plane waves that propagate. But in a way, that's not really realistic compared to what happens in the ocean. The wind doesn't just generate waves in one direction. So one way to approximate that a little better is to say, okay, the wave can actually, the wind can actually blow during the storm in any direction and creates wave in any direction. So yeah, so that maybe an axisymmetric wave would be a better way of describing what's happening in such a situation. So that's what we did here. We decided to study, to create a generator, to build a generator that would create an axisymmetric wave. So that's the generator. So we use the same system of cams on a shaft that's rotating, except instead of having these rectangles here that we use as part of the wall, we actually attach a cylinder to two of them that move, of course, in phase. And so you get something that looks like this, and when it moves, it looks like this. So it's really the surface of the ocean that's agitated. So it's an ocean that's very nice because it agitates, it creates a Bessel function. So it's very, very ordered ocean, because this profile here is actually a Bessel function. The Bessel function is actually the plane wave in an axisymmetric environment. But of course, we can do other profiles, and we actually did study other profiles. One thing we studied was focusing wave energy, because if you have an axisymmetric system, you can actually have two waves generated or a cone generated. That's of course symmetric. And in this region, you have a focalization of the wave. So that's one thing we studied. So this is an analytic calculation, but in the experiment, you actually get this. So it's not as nice, but that's because here you actually have, because of the enhancement of amplitude here, you get instability gain, where the analytics did not take that into account. Just an analytical calculation of the production of the waves. And in this region, again, we saw this famous, the TRI that I will talk to you about. So it's a way to generate an enhancement of amplitude and more instability. Another thing we did was, I'm going back to this slide, because if you put some walls here, which can happen in the ocean, and the wave can be actually trapped in a region, then instead of a wave, you will have a mode, right? Because it will trap and go back and forth between the walls, and you will have what people call a mode here. And so that's another type of study we did. We studied axisymmetric modes. So we used, again, using this profile as Besson function, which is simple to describe mathematically to use mathematically for axisymmetric cases. So you have a mode 1 where the profile of the or half the profile of the generator looks like that. There's of course the other half that's symmetric here, or a mode 2 or a mode 3. And when you actually look at the waves, that's what you have. So you have that's the vertical velocity, that's the radial velocity, and that's the radial velocity, but seen in a horizontal plane. These are in the vertical plane. So you have again your mode 1, mode 2. Yeah, radial mode 1, mode 2, mode 3. Well, these are just the actual measured radial dependence of the wave, and it's actually fits nicely to a Bessel function anywhere in any depth in the water. And so these modes can resonate. So it's not this time it's not the trial resonant instability. It's a simple linear resonance due to the fact that the mode propagate vertically, but it's within a confined height because they reach the bottom and then they come back. And so there's not only a radial confinement, there's also a vertical confinement. And so again, with the three types of mode, so you fix a horizontal wave number that's fixed by the generator. So that's a wave number, that's one. And the vertical wave number is fixed by the horizontal wave number and the frequency through the dispersion relation. So you get actually this relation here between vertical wave number and horizontal wave number, implying the n omega to a frequency. And so there's a vertical confinement that sets a resonant condition. It means you can only, to actually get a resonance, you have to have an integer number of half wavelength in the height of the tank. So that's very simple, just like the rope. When you oscillate a rope and that's attached at the other end, you get the same phenomenon here. And so that's what we see here. So what do we see? That's the maximum amplitude of one velocity, so the vertical velocity, normalized by A omega, A the amplitude of the generator, omega the frequency, and versus omega of n. So the theoretical amplitude, you expect divergences, so it's supposed to diverge to infinity if there is no viscosity. That again corresponds to trapping the wave on a length that's an integer number of half wavelength. So you get all these possible maximum here, and the dots are the measurements with two different amplitude of the generator, 5 and 2.5, and you see that it follows quite nicely so you actually see the enhancement of amplitude in these regions where it's supposed to happen. Of course, there's viscosity here, so it will not go to infinity, and there are regions where we actually observed so it's called nonlinear region. What do I mean by that? Well, if you take an experiment here, it looks like this. So it's nice, and you see again. So that's time, and that's that's the amplitude that's measured. And so it looks nice. And sorry, it's the velocity that measured again, the VZ. You see your wave propagating nice and. So it's probably there are regions where there are times where it's less intense. That's probably because it's not exactly at the resonance here. So you get some beat phenomenon. But if you take now a case here in this region, because of the larger amplitude due to the resonance, you get this nonlinear behavior. It means you get the appearance of again a more complex structure. Find that again there is a nonlinear behavior and nonlinear instabilities that take place here. We also looked at transmission through a buoyancy interface. So here we have we studied the case where you have a change, as I mentioned before, a change of the slope here, meaning a change of n. And when you propagate waves here or a mode, you actually see the difference. The wavelength gets bigger here because you change n. And again, the wavelength, the vertical wavelength is imposed, I showed you the equation, by the horizontal wavelength and the value of omega and n. So omega doesn't change, but n changes from here to here, so you get the different wave. And we try to compute how much of this wave will actually go through. So it's called the transmission coefficient. Here, the amplitude of the wave after this line divided by the amplitude of the wave before. So maybe because for the sake of time, I won't go into details about these two cases. I will just show you the result. So here it's a transmission coefficient, so measured for the waves, and this is the one computed, including viscosity, as a function of frequency. So it means there is one frequency at which the transmission through this interface here works better than others. And it happens to be actually the frequency at which the bottom waves become evanescent. Because the bottom wave, since n is smaller here, you can have cases where the wave exists here, but it has an n omega that is larger than n. It's smaller than n here, but it's larger than n here. And the threshold between the cases where omega is larger than both values of n, so it's here, and the case where omega becomes lower than n here, sorry, larger than here, this part here, and that corresponds to the maximum. So we try to apply that to real ocean. So that's a measurement of density versus depth made during a cruise in September 2018 to which my PhD student Samuel participated. The cruise was called Soda, and so you have two different values of slopes here, which bring again two, as I was saying. In reality, you have two different values of n. And there's of course an interaction, a certain thickness of the region in between, and so we try to compute using this profile. What could be expected here. And rotation also plays an important role in the Arctic, it's high latitude. So here we are in the case where F is actually different from 0, and we are in this situation here. And what we get, so that's again the transmission coefficient as a function, this time not of frequency, but of horizontal wavelength. So 2 pi over L. L is the horizontal wave number. So because it speaks easier to understand that. So that's the wavelengths in kilometers. So for high frequency waves, you can see that there are enhancements, again, due to enhancements of the transmission at certain wavelengths. For higher frequency, lower frequency waves, which are near initial wave because they are at a frequency close to F, and so they're called the near initial wave. It's mostly the large scale waves that can have an enhancement of transmission through the interface, and the small scale wave almost go through with no enhancement. So that's what I was saying. Last point I wanted to mention was again, trying to assess mixing induced by internal waves. So this was the work of Ivan Dossman as a postdoc. So there's a limit you can do with synthetic Schlieren in a mixing environment. So that's an example here. So you have your generator here. You see again the motion of the dots as before, except that after a while it becomes blurry, and the blurriness grows in your field of view. And why does it become blurry? Well, just because you create mixing so that actually you mix fluids that have different indexes of refraction. So you get this blurry thing just in the same way when you look at the sky above, just above the hood of your car that is hot, you see the same phenomenon here. So that's exactly what's happening. So we decided to use another, so you cannot really measure when it mixes, you cannot use synthetic Schlieren as we used before. So we use another technique called PLIF, so it's planar laser-induced fluorescence. So you use a fluorescent dye, and you actually stratify your fluid with the dye concentration in the same way you stratify it with salt, so that the dye concentration is a proxy for the salt concentration, or in other words, for the density. And the dye concentration gives you a certain amount of emitted light, because it's a fluorescent fluorescent dye, sorry. So the amount of light that is emitted is a proxy for the density. So you just measure the amount of light that is in place, and it gives you the density. So you have here, so that's a raw image, but that's not density, of course, because that's because you have the laser comes from here, so you have more intensity here than here, and that is not due to a difference of density. It's due to the fact that the light gets absorbed on its way. Of course, if it's re-emitted as a given, if it's re-emitted by the fluorescent dye, it means it's absorbed, and so you have to correct for that. But at the end, you get something, and we also measure PIV, measured velocity using PIV. That's a mode 1 wave, and so that's the kind of result we get. So the arrows that move here are the velocity field, but what I'm interested in are these color lines, which are isopycnal, so lines of isodensity, and they move once the wave is propagating. They move following the wave. But the interesting thing is that after a while, you start seeing that some of them will overturn, especially the green and the yellow one here, or the orange. You will see nice overturns, just like a wave when it arrives on the beach. It overturns, and so that's what we're looking for, because if it overturns, it can create mixing. So coming back to this slide I showed you a long time ago, we said, okay, now we can measure density, we can measure velocity together, because we have the PLIF and the PIV, and so we can actually compute this quantity directly, and we know this one, so we can compute KT. So that's the whole idea, measuring the turbulent diffusivity in the experiment. So first, the case when there is no instability, because this is related to the instability. So the velocity field looks nice, and you have these vortices that move. That's typical of a mode 1 propagating, and that's the field of KT that we measure. And you see nothing. It's green. It's 0. Of course, it doesn't mean it's 0. It means it's below what we can measure, but that's okay, because what we are interested is what happens in the case where you do have the instability. Sorry, that's that's the wave. Here looks nice and sinusoidal as expected. But here is the case with TRI, so with instability. So at different times, you see the wave field looks different from before, especially as you go forward in time. Here, you have TRI and stability. And here, nicely, you see that there is a region where the actual value of KT gets beyond this 0 value, which was just the limit of what we could measure. And it gets to the order of 10 to maybe 20 millimeters square per second. So that means it's 0.1 centimeters per second. So it's 10 times smaller than what's expected for the ocean, but again, it's a small tank and it's not the same magnitudes, of course, especially the sizes are different, but it's still like 1,000 times larger than molecular diffusivity. So we actually have a measurement of turbulent diffusivity here, and it shows that it's spreading through the tank. Now the thing is, what happens at long term? Because this is not long term. This is 26 times the period of the wave. That's 4 minutes. So that's not a lot. And if you wait longer, it becomes more difficult because of the mixing to actually measure something nice in terms of waves. So we found a different way to do that. And I'll finish with that. So here is a series of measurements of the density profile with time for a much longer experiment that lasted 3 hours. So initially it was this blue straight line because again we had made this nice linear profile. And with time you see that the straight line deforms in the way that it gets more vertical here, and more vertical means lower end or more mixing, because of course if it's completely vertical, it means density has one single value on all at any depth, so that's completely mixed. So the more vertical it becomes, the more mixed it becomes. So clearly there's mixing happening, and because with time it gets more and more vertical. The last one is after 3 hours is this bluish line here. So you can try to actually measure some things here. One thing you can do is compute the potential energy, because again, that's what was in my introduction. You're trying to convert kinetic energy, that the energy of the waves, into potential energy, which is changing the background density. So you just compute the kinetic energy here, the potential energy here as a function of time. The potential energy, of course, is defined at two constants, so I will start 0 here corresponding to the straight profile, and you actually see that you gain a little more than a joule of potential energy during. So that's during, that's even much longer than that. That's just an example here, but we did the experiment for about 20 hours. So you actually increase the potential energy in the tank, and you can try from that to estimate the mixing efficiency, which would be the amount of potential energy you create divided by the amount of mechanical energy that you input by generating the waves. And so this can be computed. So of course we don't measure pressure, so you can't compute that directly, but there is a proxy to actually, just by having the velocity field, measuring the total energy of the wave field. And when you make this ratio, with time it seems to be constant and of the order of 10%. So 10% of the kinetic energy is actually converted into potential energy by this mechanism here. So I'm finished here. I won't read through this huge list of things. You can read it yourself and ask questions. Maybe a few points about this. So we'd like to do a little more on measuring turbulent diffusivity and the link with mixing efficiency, because these were really preliminary results that were actually done at the end of a thesis or a postdoc. So we decided to hire a new PhD student who started this September, Julie. So I'm supervising her with Sylvain Dubourg, and more results on this measurement of turbulent diffusivity and mixing efficiency, especially as a function of different parameters of the waves and so on. And there is also I haven't talked about that, but there's one way of measuring mixing using the scales called the Thorpe scale. We haven't tried that. That's promising. So this is the kind of things we'd like to do during the. Thank you very much.
Are there any questions? Okay.
Yes.
Sorry,
Yes.
So let me go back to
You mean? So I'm missing one word. The R?
Here.
Yeah.
the triadic resonance institute.
Triadic. Okay. If we see the triadic resonance here, well, so when I showed, so let's see. I don't think we did in this case. We were really trying to maintain things linear, and so it's you would probably see it in regions where it's enhanced. So maybe yeah, when you have an enhancement of transmission coefficient. But again, you cannot have, of course, you cannot have more energy here than you have here. So yeah, in general, we didn't see general. Yes. Yes.
What's the basis? Did something about that?
No. The Hilbert decomposition just a tool to actually extract in an image what belongs to a given frequency and what belongs to other frequencies. But the fact that the three wave vectors actually add up to zero, that's inherent to the instability. That's if you write the equation for the instability, you actually end up seeing that the only case where you actually get a large amplitude in this interaction between three waves is the case where the three wave vectors are somewhere.
And there's the short wavelengths, once they are suppressed, the instability doesn't happen.
Well, yes, but it's the other way around. I would say it's the short wavelengths appear thanks to the instability. Yes.
So that vector activity, that will be valid even for a non-linear case for the triadic resonance. And some of these vectors,
Yeah, you do that, but then at least one of them, so that's getting better.
so some of these vectors in the triadic resonance will be valid for a non-linear case as well.
Well, that's non-linear. That's the instability itself is a non-linear because if you have an interaction between two waves, it means there is non-linearity.
So your amplitude is tiny. Right? When you increase your amplitude, you said it goes into a more non-linear regime.
Yes. When you increase the amplitude, so that's maybe we were able to see that. No, I didn't. I don't have a slide where I show that, but yes, there is one. If we look at this slide here, you look at this slide here, you see that. So, yeah, no, it's tricky, but actually, yes, in a way you can see that. I'll explain that. Red is measurement at large amplitude. Blue, it's a smaller amplitude. So you could say, oh, it's strange because the large amplitude, we see them here. And the small amplitude, we see these dots here. And the large amplitude seem to not appear in the region. But the reason is because it's a large amplitude, it's more likely to have nonlinear behavior. And when you have nonlinear behavior, you cannot measure the amplitude anymore. So in a way, if it's a large amplitude and you have instability, then you cannot measure it, and that's why we don't have red points here. Actually, we do have red points, but we were not able to measure them because here what you're trying to measure is a velocity, and because that's this axis here is a value of velocity, and if you look, I think I must have somewhere this velocity. So it's a different example, but it doesn't matter. Where is it? I have the amplitude of the velocity. Yeah, here. So here. So that's, again, that's the velocity. So here you have no instability. You have a nice, so it's not a sinusoid, it's a Bessel, again, the axisymmetric situation. But from a signal like that, you can measure the amplitude. When the signal becomes much complicated because there's instability, you cannot measure the amplitude anymore. That's why you don't have response. So in a way, it's a way to answer your question. When you increase the amplitude, you are more likely to see
Any other questions?
Yes.
Stratification which has a break.
Yes.
And two linear. So it's the same method.
It's the same method, but a little cleverer. In the sense that in the double bucket method, what you do is that there is a constraint, a strong constraint on the flow rates, because you simply have these two things communicate through this pipe, so that each time you extract, say if you extract a liter per second, that's a lot, say a milliliter per second from here, it means that you have half a milliliter per second from here that goes here. That just because you have this relation and these two levels have to go down at the same velocity. So actually the milliliter per second you extract from here, you could say it has to come half from here and half from here, so that this flow rate has to be half a milliliter per second. And you can actually show in the equations that if this flow rate is twice this flow rate, you get the linear profile. But now what you can do is, instead of putting just a pipe like that, you put a pump here. And you control the two pumps independently, and then you can get something different. So the example I showed you, it's not really a nonlinear, it's just that you have a different slope, and then you change some parameters of the pump and you get another slope. But you can also, we also did cases where you have an exponential profile. You can do anything you want, but what you need is at least one. No, one is enough. One pump whose flow rate is controlled by the computer. The other pump can go at constant speed, but one pump is controlled by the computer.
Any other questions? Okay, there are no other questions. Let's thank Philippe. He'll be here with us for at least a couple more weeks. So if anyone is interested in having further discussions with him, please feel free to contact me on and Thank you.